If you've been feeling lately like you need an escape from all of the bad news happening here on Earth, then this is an episode for you. Today we're going to look beyond Earth and even our solar system and talk about exoplanets. What planets lie beyond our solar system? How different are they to the ones around us here? And what light do these exoplanets shed on the ultimate question of whether there's life elsewhere in the universe? Today we have on a very special guest who will give us the lowdown on all of this and more, so stick around.
This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a fan and regular consumer of Wondrium's content for the last 15 years or so. Over that time, I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and science. For me, it's like taking an intro-level university course from a great professor on a subject you've always wanted to know more about, but without the big tuition fee and all in the comfort of your own home or daily commute. A few years ago, I wrote and presented a series of lectures for Wondrium called What Einstein Got Wrong. Over those 12 lectures, I described some of Einstein's biggest blunders and mistakes. These included misconceptions that he had about things like black holes and gravitational waves, as well as his failed attempts to find a grand unified theory. So if you want to get a more complete picture and maybe a more human picture of Albert Einstein, or to learn about just about anything else, check out Wondrium and give them a try. Sign up now through our special URL to get a free month of unlimited access. Just go to wondrium.com/universe. That is wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. So we're very happy to have on Why This Universe this week Diana Powell. She's an expert on planets that lie beyond our solar system, what are known as exoplanets, including how they form and how they evolve. Right now, she's a NASA Sagan Fellow at the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. And she got her PhD just last year from the University of California at Santa Cruz. And most exciting for me, she'll be starting in 2023 as a Neubauer Family Assistant Professor of Astronomy and Astrophysics at my very own University of Chicago, putting her office just around the corner from my own. Welcome to Why This Universe, Diana.
Thank you so much for having me. Great to be here.
In your mind, in your words, what's the big picture view of planets, of exoplanets? What do we know at this moment about these objects? How common are they, and what do we think they're like?
Yeah, so big picture on exoplanets is that we think they're very diverse and that they occur really frequently. So current estimates are that stars in the Milky Way on average host around 2 to 3 exoplanets for every star. So we think there are billions of planets just in our Milky Way alone. And what we know about them so far is that they're very diverse. So actually the most common planet in the galaxy is a planet that is very different from the ones that are in our solar system. So something that we actually don't have. They're called super Earths or mini Neptunes, and they're something a bit smaller than our Neptune or Uranus, but also closer to their host stars. Some of them might be kind of like small Uranus and Neptune. Some might be bigger than Earths. And really big picture with planets now. So we know they're common, we know they're diverse, we know the most commonly occurring planets are not ones that we host in our solar system. And we've been entering this really new age of exoplanet formation and evolution understanding. So now we can really see planets forming, we can see their atmospheres, we can see them in rich detail, so more beyond just their demographics.
So 2 to 3 exoplanets per star, like you said, that's a big number, but we've got 8 in our solar system. Should I be surprised that it's so much smaller than that?
I think no. So, one thing that we know is common about stars that aren't our sun is that many stars are in binaries in multiple systems, and it's actually kind of surprising that even stars with such dynamical interactions host planetary systems. But then the number now, I should say, I wouldn't be surprised if that goes up as our sensitivity to planets at larger radii increases. So right now we can really look at planets just to a few AU, so a few times the distance from the Earth to the sun. But right now we can't pick up, or we're just starting to pick up to be able to detect things like Jupiter, and really things like Saturn, Uranus, and Neptune are beyond our detection range at the moment. So I would not be surprised if that number increases. That's just based off of current demographics.
Yeah, so maybe a doubling or something as these telescopes get better.
Yeah, yeah.
So, like, speaking of telescopes, like, what are the big players in the game right now? What are the telescopes that you keep your eye on the data of the most?
Great question. So we're at this transitionary period. So next week, the James Webb Space Telescope will launch, and that will totally revolutionize the study of exoplanet atmospheres. So I have my fingers crossed for that, and that could totally change how busy my career looks like for the next decade.
Since this recording, JWST has been successfully launched, so Diana's career is safe.
But right now, I still keep an eye on things coming out of Hubble. So Hubble, the earlier James Webb, still does a lot of the really rich atmospheric observations that we see. There's some really nice ground-based telescopes that do work at high resolution, so I also pay attention to those. Some of those are like the HARPS North, but really also the Very Large Telescope. So that's out of Europe, and they do some really great imaging and high resolution atmospheric studies of large planets that are further away from their host stars. So I'd say they're kind of approaching the border between stars and planets, things that we can see in high detail now. And then the telescope that's coming out that I have to mention is TESS, the Space Telescope. So that's looking at a lot of the bright nearby stars to really characterize the planet that we're seeing around those stars. I think it's at least once a month there's some planet that comes out of TESS that is really unexpected.
Give me an example of what an unexpected planet looks like. What makes a planet more or less expected to an expert like yourself?
Yeah, great question. So something like a very dense planet, very large and dense, is something that's unexpected. So there's been some talk of things like super Mercuries, like very dense planets that are very large. So that's unexpected. It probably points to some really interesting formation pathways. And that's not something that we've necessarily pulled out of too many surveys. So really dense planets, planets that are in regions of phase space that we don't think are likely. So something like a really big gaseous envelope in a region where we expect that a star's activity would blow off most of the atmosphere, but sometimes they persist. So a planet that lies really separate from, like if you look at like mass radius, something that's really unique from other planets that are like it. So I'd expect it to have much more atmosphere, much less.
So let's unpack some of that a bit. So in our own solar system, we have a few planets that are pretty small, mostly made of rock and dense near the sun, like, Mercury, Mars, Earth, whatever. And then you go out farther and you get these big puffy gas giants, or maybe ice planets or something. But you're telling us that what these telescopes are finding are planets that don't neatly fall into those categories. Is that about right?
That is about right, but I will say there's plenty weird about our solar system. So it looks like
Okay.
the more common solar systems have densely packed planets, much closer to their host stars than our Mercury. So really, our solar system has a very empty inner solar system. So we think of Mercury as close to our host star, but for some of the planets that we see, you could fit whole solar systems interior to Mercury's orbit.
And is that just like a throw of the dice that our solar system happens to be an oddball by chance, or does it tell us something about the history or how our solar system formed compared to other solar systems?
Yeah, it's a good question. I think there are a lot of theories around this going around right now. I do think that our solar system is still difficult to detect, so we might find that we're not as rare as we think we are now. But I'd say it's not quite clear. So there's some studies that indicate maybe our sun was really active and cleared out the inner solar system of planet-forming material at early stages.
What does it mean for a star to be active?
Yes, so I think of stars as being active where well, I guess a variety of causes could lead to it, but where they have things like stellar flares, maybe they're outflowing mass or high energy of radiation. That could be due to something odd going on with their magnetic field. And our sun does seem like it might be a little bit magnetically odd compared to other solar type stars. It's less active right now, but in terms of how it was in the past, it's hard to tell.
So let's take a step back from the global picture of research in this field and tell us a little bit about what role you play in it. Like what's your specific research on? What do you spend your time thinking about?
Yeah, so in terms of questions, I keep those pretty large. So I'm really interested in how planets form and evolve and then what they look like today. So I spend a lot of my time thinking about the environments of planet formation. So these are protoplanetary disks, which form as the host star forms, and they're large disks. And when I say large, like 200 AU, several times the size of our solar system, and they're full of gas and dust, and that constitutes the material from which planets form. And a lot about planetary systems is set at this early stage. So half of my research is how planets form, well, really the environment where planets form and how that affects how they form. And then half of my research is the atmospheres of planets, extrasolar systems, when they're more evolved or when they're young. And I really want to tie their atmospheres and what we can learn from their atmospheres to the disks and what we can learn about the disks. So fairly broad, but and then something that connects the two is what turns out to be really important on these large scale systems. So large disks, large planets. I end up caring about things that are micron or centimeter sized, small dust grains that tell us a lot about the systems that we're observing.
The picture, as I understand it, is for many decades, astronomers have speculated quite reasonably that our solar system, before there were planets, we had a big disk that extended out to the edges of the solar system, and that state persisted for a little while until that the stuff in that disk either got expelled or fell into a star or congealed into these planets. And now we actually have telescopes that can actually look at other solar systems that are actually in this protoplanetary disk phase. Is that right?
Yes, so now we can look at the disks themselves, and this is quite new. So around the time I was being born, like 30 years ago, we didn't know if disks existed or not. People thought star formation might have been perfectly efficient. But we now know that these disks exist. We can see them, we can see their structures, and we can even see planets forming in the disk.
How many have we seen?
How many planets have we seen in disks?
How many protoplanetary disks?
Oh, protoplanetary disks. Oh, good question. I think in really, really high detail where you can see lots of these features, we're in the like 10 to 20, maybe 30
Okay.
range. But total disks, probably around 100 or so.
Okay.
Um,
Okay.
well, much more, I guess, if you can't resolve the disk, not looking at it directly, but looking at a stellar, emission being absorbed from the light from the host star at infrared wavelengths, then yeah, probably on the order of hundreds.
Do you have a favorite exoplanet that's been discovered?
Oh, yes. It's hard to choose just one. But there's ones that are very useful for my research. Maybe I'll do it in terms of class. So I'm a theorist, so it's hard. Well, I could choose a particular one, but I love really hot Jupiter-like planets right now, and that's because they have really amazing data, and we're learning a huge amount of physics from their atmospheres. So really, really massive hot planets that have really energetic atmospheres, lots of mixing, lots of different objects forming, lots of different species forming clouds. Um, Magnetic fields are doing interesting things. Lots of stuff happening in their atmospheres. That's really interesting physics.
So whenever I start thinking about exoplanets, it doesn't take much time before my mind is wondering to the possibility that life might exist on some of these planets. If you take what we've learned about exoplanets in the last, I don't know, decade or decades maybe, how does this change what we think we know or don't know about the likelihood that there is life on planets other than our own Earth? And, what could we say about the kinds of planets that life might emerge on, or maybe the likelihood or quantity of life or abundance of life that might exist elsewhere?
Yeah, so I think the field is really focused now on life that we can detect. So I think, well, me personally, if I just look at the number of planets out there, and if you look at extremophile life on Earth and the persistence of life through things like if you shoot an asteroid into space and it explodes, you don't kill off the life that's on that asteroid. So it seems like life, at least once it takes hold, is pretty persistent. So I personally am quite hopeful that life exists out there. But then it's can we observe it? Can we see it? So something in the favor of observing life is that there are so many planets. So it's not so rare that we're on a planet. That's a common occurrence in the universe.
So the basic elements there are that life seems very resilient. It can live in places that seem hard to live on Earth. And you said something about when we put asteroids with life into space, the life survives. I didn't know that. How do we know this?
Yes, so there's some very interesting lab experiments that I know about this, where if you subject, like you have a normal rock, something that could So I'll start by saying, even in our solar system alone, the planets in our solar system exchange tons of rocks if you do the order of magnitude estimate. So we have rocks from Mars, Mars has rocks from Earth, and that extends throughout certainly all the terrestrial planets, but even further out, we expect that there's significant exchange of material.
It sounds very counterintuitive.
Yeah, it does sound very counterintuitive. So I don't know all of the exact dynamics of it, and I have not done this estimate myself, so I probably can't give you the most satisfactory answer. I think it's rather intuitive to think if you have something that outflows from the outer solar, well, something like Mars inwards, the inner solar system, you're more likely to be funneled into the star, expelling things outwards a little bit harder for me to imagine. But I think it's more small scale, steady state interactions. There must be a nice order of magnitude problem to do here that we should think up.
But like, let's say I have a piece of rock here on Earth. How do I get it out of Earth's gravitational pull? I mean, it has a 11 kilometers a second, escape velocity. It's not every day you see a rock moving at 11 kilometers a second. Like, so, how does that happen?
Yeah, so not every day. So my guess, not having done this and really taking people's word for it, would be something like an impact that would blow up debris into the outer parts of Earth.
So some sort of meteorite comes in, or meteor comes in, strikes a planet, breaks some of that planet up, and throws it into space. Okay.
Yeah, that's my assumption about this calculation. Again, not having done it, must be something with impacts and then calculating how much that debris is exchanged. But it does motivate these lab experiments, which I know happen, where people take a rock that has some amount of bacteria or something on it, really like a natural level of what you might expect on an Earth rock, some coating of life. So really, if you look at anywhere on this planet, there's tends to be some kind of life around. And they subject it to a vacuum, and then they explode the rock. So it's in vacuum, space-like conditions. It's really cold. Then it undergoes an explosion, something maybe that simulates a giant impact. And then if you go after this has happened and you see how much life has survived, the whole chamber is coated in bacteria. There's bacteria everywhere. Somehow they don't die. I mean, I think it kind of naively, I would expect things to die more easily than that. Certainly, if you did that to a human, we would die. But not all life is as sensitive as us.
So can we take everything you're telling us about exoplanets and the recent discoveries, Diana, and put it in something like the Drake equation's terms? So I'll just remind the listeners that the Drake equation was put forth by this important radio astronomer, Frank Drake, back in the late 50s. And he said if you multiplied a bunch of numbers together, you would get the probability that you could detect intelligent life using radio telescopes. So the first several factors of the Drake equation, I think we have a pretty good handle on now. The rate at which stars are being formed, we know that very well. The fraction of number of planets per star, we know pretty well, or at least reasonably well. The next is how many of them are what we call habitable. So how many of them have like the potential to have liquid water? I think, at least within a stone's throw, we have that number down. And then after that, I think it gets a lot, less certain. Diana, do you want to comment on your thoughts about some of those other numbers and maybe what our most reasonable estimates for these might look like?
Yeah, so the fraction that's habitable, I really think, oh yeah, so for liquid water, we can begin to get a picture of this. For what's habitable, I think is still quite unknown. So I'll say that it's still quite a debate in the field whether we'll find life outside of our solar system or inside of our solar system first. So just in terms of life, we don't know that there's not life here on nearby planets. We have a pretty good idea that it's not intelligent, or if it's intelligent, it's not intelligent like we are. So we don't see cities in the Kuiper Belt, although people have written papers about that recently. But you could find life there. And so if life is in other places in the solar system, then we know it's diverse, and it might be very different from life here. So the conditions for life were not quite known, not exactly, although people are working on this and thinking about life that could be very different from us, and what kind of chemical signatures it might produce. So that's an active area of research.
So before we go to the exoplanet life possibility, where in the solar system, if one had to place a bet other than Earth, might it be most likely that life could exist?
Yeah, so I think my biggest bet would be for someplace like Enceladus. So these are icy moons that have subsurface oceans. We know because they have plumes that outflow, and so that's liquid water. Well, they're actually salty, so it might be not something so different from our own oceans, where we think that life may have arisen here on Earth. So that's a promising prospect for life. And I think if you talk to most planetary astronomers, they might bet Enceladus first. But it's not just Enceladus that we're looking at. So Europa is also a similar planet. We're sending the Europa Clipper out to check out Europa soon, and it'll fly through some plumes. There's a funny story about why we're going to Europa and not Enceladus, although astronomers might choose Enceladus. But apparently some congressman was like, no, it has to be Europa. And so we're going to Europa.
Why is that? Was there any reason?
What was the reason?
I heard through the grapevine, not directly, that it was a dream that he had. But I think it might have been very Stanley Kubrick inspired dream. The 2001: A Space Odyssey book series, eventually they go to Europa because life is there. Either way, it should get really interesting information. But so Enceladus is a big prospect for life. People have not ruled out entirely life on Mars. Well, I think there's really interesting potential evidence for an earlier biosphere on Mars, but there has been some anomalous methane detections. I think the field is leaning towards that those detections maybe not being super robust, or possibly if they are there, it's some very abiotic explanation. But it's possible. So excess methane on Mars, people think about that. Then there has been recent flurry around Venus and the potential detection of phosphine in the clouds of Venus. Phosphine is thought to be something that's outside of really massive planets, not something you'd expect to be produced in abundance, but people are working on that. And then also, if you look at Titan, so Titan is also a moon of Saturn. And it looks, just from pictures, like if you look at a picture and make it black and white, it looks like you're looking at Earth. It has a liquid cycle. It's not water, but it has liquid lakes.
If not water, what's the liquid made of?
Ethane and methane. And so the reason people are interested in Titan is that there's a lot of rich hydrocarbon chemistry. So things that we think like carbon chemistry could be something that makes you think of life. And we know from things like Cassini had a probe that landed on Titan that there's really, really complex, large hydrocarbon material in the atmosphere. So large that the mass spectrometer aboard the probe did not detect out to the limit. So really, really large molecules that we were not expecting. And all of that makes us think that if life is really diverse, so if there's life on Titan, it'd be very different than life on Earth. But if life is diverse and has different formation pathways, then that's another promising place to look for life. And we're also going out to Titan soon, Dragonfly. So all of these things will be checked out. But if I was putting money somewhere where we're going to find life first, I would still bet exoplanets over the solar system. We've been looking at the solar system for a while, and I think I like to feel really convinced that there's life out there. You want some big whopping signal, and that could be out there waiting for us on exoplanets. We just haven't had the capability to see it yet.
Let's put some money down here. What are the odds, in your humble opinion, that there's some sort of life beyond Earth but in the solar system? And then what is the separate odds that there's life beyond Earth but in the Milky Way? And this could be any kind of simple life or whatever. It doesn't have to be, mammals or something.
So I'm a life optimist. I'm not a betting person, but if it's life outside of Earth in the Milky Way, I bet like serious money on that. So I would put odds at 99%. I think it's out there. In the whole Milky Way is a big area. Yeah, that's a lot of stars. A lot of planets. Some kind of life out there. I'd put big odds on that.
What about in the solar system?
In the solar system, yeah, so I'd be quite a bit more conservative, although I'm optimistic. Maybe 10% chance that there's nice life. Well, I don't know. We had exchanged, like, it's much more likely that you do have some Earth microbe hitching a ride to Mars and being able to exist. So life that started separately from Earth, not so likely, but yeah, maybe 10-20% chance of life. I still think that's fairly high.
So you think the most likely way that there would have been life outside of the Earth but in the solar system would be it starts at Earth, a meteor hits Earth and breaks up at Earth and sends some chunk to Mars where it catches on board there, or picks up from there. A common evolutionary chain.
I think it'd be hard to rule that out. If we find life somewhere else in the solar system, it'd be very, very hard to rule that out. Just because we know life on Earth is so persistent in so many extreme environments. So extremophiles are these type of life on Earth that live in like hydrothermal vents on the seafloor, or in these intense volcanic areas in Yellowstone National Park. So if you ever go there and you see around the vented pools of water, like hydrothermal vents, well, I guess, but above the ground, you see like very beautiful colors around the edge of these things, and that's all extremophile life. So just because it's so persistent throughout Earth and in very different environments, I think that it'd be hard to rule it out. Although I'm not, it's totally possible that at early times Mars and Venus were habitable much more like Earth, and they could have given rise to their own biospheres that formed independently from us. Um, yeah, no clear way to know. But if we do find life on in the solar system, it could easily have started from Earth.
So going back to the Milky Way as a whole, you said you think it's something like a 99% chance that there's life somewhere out there. If we restricted it to, like, say, multicellular life or some sort of complex life, well, how does that change your odds? Do you think the odds go down a lot at that point?
No, I think that for me, the odds start to go down once we look at life that's more advanced than us. Maybe you have some, well, maybe we're approaching a bottleneck, and that's one, the Fermi paradox, which I actually really think, the Fermi paradox is like, if life is so abundant, if there are aliens everywhere, why haven't we seen them? But I personally don't think we've looked enough to know if we've seen them or not.
So you just mentioned two things. Let's unpack them. So you mentioned bottlenecks and you mentioned the Fermi paradox. So Fermi paradox is this, life seems like something that should be abundant, but we don't see any like obvious evidence of super technologically advanced civilizations out doing things. Why is that? And then the bottlenecks, like I know of three popular bottlenecks people talk about in this context. They say, well, maybe, getting life started is really hard. And that only happens in one out of some very, very, very large number of planets. So that explains why the universe doesn't seem to have life except for the place we happen to live. Some other people, I guess, have argued that the main bottleneck might be going from simple single-celled organisms to complex multicellular organisms. And maybe that only happens, one out of a trillion times or something. And then a third bottleneck I hear talking about is when roughly where we're at, which is what you were alluding to, Diana, when civilization gets technologically advanced enough, their technology ends life on that planet, or at least ends the advancement of technologically advanced life. It sounds like the third bottleneck is the one you think is the most compelling as a resolution to Fermi's paradox. Is that right?
Well, yes, mostly because I'm not a big fan of things like the anthropic principle. So I tend to not like to think of us as being super rare things that don't happen in the universe. So we exist, so maybe other things like us exist. There's 200 billion stars in the Milky Way, factor of 3 more planets. In our solar system, we know for sure that out of 8 planets, one of them took life. I don't know. So I tend to be against the idea of, oh, well, life is super rare. We're alive though, and the only reason we can ask the question about life being rare is because that happened. I don't know. As a well, some scientists love the anthropic principle,
But by definition, if life was super rare, all life would be at the one place that it was found, right? So that's logically self-consistent. Yeah.
It's true. But I tend to get uncomfortable with the really fringes of this is super rare. I also feel that way with things like planet formation. Like if you have to appeal to something very fine tuned, then I want to find a bigger, broader picture that makes more sense of things in ways that doesn't make a specific thing very rare if you haven't observed a lot of things. So I guess I'm just not convinced that we're rare. So I'm more like inclined to believe, and really this is belief and the way I like to think. I'm more inclined to believe that life could have existed elsewhere and gotten to at least our stage. But yes, I'm not sure if life could be much more intelligent than we get to. Maybe we just contribute to a mass extinction event. Life goes back to square one, and you have these cyclical patterns of life overshooting and going back to a stage that's not so technologically advanced. I should say, so we haven't seen conclusive signatures of techno signatures. If we had, that would be very big news if we were all convinced. But we have seen things that possibly could be techno signatures. It's thrown out there every once in a while. We see like weird light curves from stars where they dim and brighten at odd times in ways that are hard to explain. People appeal to things like swarms of comets. But you could also imagine something like a Dyson sphere that's harnessing power from the star. All of that is not conclusive to me personally, but it's not completely impossible either. Yeah, it's actually hard for me to think of what would be conclusive evidence of really technologically advanced life out there. That's a question that keeps me up at night. If we saw it, how would I be convinced?
some sort of contact, like coded message or something, I suppose.
Yes, yeah, that would be convincing, but that would also be incredibly difficult. Space is big and coherent signals are hard. So,
As the Sagan fellow, I guess you have to, endorse his books every once in a while, right?
I do love Contact. If you haven't read Contact, I think it's a great book. So that would be conclusive proof for me. Um, one of the things at the end is the aliens tell them that their version of God is that there's structure in pi, and she calculates pi out to a very long extent and gets a circle of zeros and ones, and learn that from the aliens. So that would be more conclusive for me.
I was just curious, you as an exoplanet scientist, if you got into this field because of this question, because you were interested in like life in the universe and outside of Earth, or if you got into it through the like just being interested in planets themselves.
Yeah, so I think that from a very young age, I learned that there were stars out there and they were really massive, and then that the universe was huge. So I think from really early on, I kind of had the perspective of, oh, most of everything that happens is not on Earth, so I have to study the universe. Um, so for me, it was really astrophysics in general and understanding of things outside of Earth. And then I became really excited about planets in particular in college. So I started college right when the Kepler Space Telescope was reporting just a huge number of detections of planets. So it ended up finding thousands of planets. We realized that they're really abundant. And then I kind of realized, like, wow, this is happening now. So I think of myself as an opportunistic scientist. So I came into fruition when astronomy was discovering a huge amount of planets. And I thought that was the hot place to be at the time that I'm alive. And I am very interested in planets for their own right, and in life. And finding that would be incredibly exciting. I think one of the biggest discoveries in human history. Yeah, so if I can be a part of this collective effort, I had to jump on board.
And do you have any fears about possibly, coming in contact or something?
Yeah, that's a great question. I tend to be not as afraid, although I know people really are. And my reasoning for this is that if you are advanced alien civilization that could threaten us by coming here in any kind of time scale, that's, I don't know. I feel like in any kind of reasonable time scale, maybe I'm a little bit cautious when we're talking about planets that are like 4 light years away from us, like quite close. But I really think if you're traversing the distance of space in a way that's highly threatening to us, then how are you so resource limited that you want to fight us for the limited resources on this planet? Like, we're already using them up. Um, for us, we're so far from having the technology to be able to travel like that I feel like there's other resources that you're using to survive. But I could be wrong, so I think it's worth some caution and some philosophy.
So let's go back to the Drake equation for a minute. We have the first terms, which we have a pretty good handle on, like the star formation rate, the number of planets per star, and the fraction of those planets that might be potentially habitable. But then we have a lot less information about what fraction of those potentially habitable planets go on to develop life, and what fraction of those planets with life have intelligent life. And then lastly, how long those intelligent ecosystems persist before they either destroy themselves or otherwise come to an end. Is there any way forward? What do we know about these things now? And is there any way forward to potentially put tighter constraints on any of these factors?
Yeah, so I agree that that's where the Drake equation gets very fuzzy. So what fraction of planets actually support life, and then how likely it is that the life can ever communicate. Um, I'm not quite sure. I mean, our development would shed some light on this. So really, I don't think we're at the stage where we're really communicating with other alien civilizations. So unless they're very advanced, they also wouldn't know that we're here. So whether or not that's even possible is a big question. So it's worth repeating that space is very large, and in doing things like communicating across long distances is not necessarily easy. Um, yeah, so paying attention to our development might shed some light on these questions. So if all of a sudden there's some major breakthrough in our understanding of the universe, and how to reach across the really vast expanse of space, then that would make me much more likely, or make me believe that it's much more likely that other civilizations have done that as well. And then if there actually is contact with aliens, or if we turn on James Webb and all of a sudden there's some whopping signal pointing out to us of some technologically advanced civilization, then that would shed some light on this. Really, I'm holding out hope in terms of telescopes for the the next generation of extremely large telescopes on the ground. So things like GMT, what Chicago will be a part of, or TMT, or the ELTs in Europe. So that's when I think we'll start to be able to really directly observe terrestrial mass planets, and we might be able to see things about the structure, the properties of their surfaces, whether they are hosting some kind of civilization. I think it'll be difficult though, probably for the rest of my my lifetime to shed more light on those terms.
Maybe if you want to talk, Diana, a little bit more about your specific research, maybe what projects you are excited about now.
So I'm really excited about characterizing protoplanetary disks and their composition. So something that we're able to do now with really advanced radio telescopes on the ground. So they're directly observing some planets that are forming in these disks, but really they're observing the disks of material around young stars. And we're starting to get a look at how the composition changes throughout the disk as a function of radius. So if you're further out from the star, what is the material like versus the inner regions closer to the star? And I'm really excited about understanding this really well so we can know things like where planets form and how they form and how they've evolved over time. So what environments have they encountered? And I think this is interesting when you come to the question of life, because once you think about terrestrial planet formation and how terrestrial planets, their early history, how that shaped what they look like now, that also might give us some insight into whether or not they could host life. So if they have to form these planets, if they had to have some really crazy dynamical history where they've been hit by many objects and shuttled around, then maybe that says something about whether or not they're more likely to form life or less likely. I mean, we know Earth is odd in that we have this giant moon because of a huge impact. So that's not quite normal in our solar system. Maybe it really helped us form life. So it's not clear which formation pathway gives rise to more or less life, but it definitely tells us something in that direction. So that's something I'm really interested in now. And then I'm also interested in understanding how clouds work on extrasolar planets. So these clouds are really different from Earth clouds, but I think that we can shed light on even cloud formation on Earth, which is exciting because clouds are the largest source of uncertainty in climate change models. And really a testbed for clouds outside of Earth, especially in these really extreme regimes, is really exciting just for understanding really phase changes is at a fundamental level. But it's also exciting for then probing what these atmospheres are made of. And all of these are lessons. So right now I'm interested in these hot giant planets, but these are lessons that we'll need when we look at terrestrial planets that will have atmospheres that are almost certainly covered in clouds. And we won't be able to see what they're actually made of unless we understand the clouds themselves, which tend to block signatures of the rest of the planet.
That's interesting that it could have the application to those like climate science models and stuff.
Yeah, that's my real hope. So one of the more immediately relevant areas of research that I would like to be pushing towards is understanding more about climates in general. So Earth climate on Venus and Mars, but also from my perspective of taking what we know about exoplanets and these really diverse worlds, diverse atmospheres, and huge numbers of atmospheres to learn really how atmospheres work on a fundamental level, which we could hopefully bring back to shed light on how things work here.
Right. It's like almost like the exoplanets are, how do you make an experiment about, different sorts of climates and what that looks like? It's like each exoplanet is a different sort of experiment.
Exactly. Yes.
Today's episode was produced and edited by me, Shalma Wegsman. My co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. Dan is also an author and has written many books, including most recently At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. Thank you for all your support and for listening to our show. If you want to support us even more, you can subscribe to our Patreon, where you can ask us questions for exclusive Ask Us Anything episodes, as well as get the ad-free versions of our regular episodes. You can find our Patreon at patreon.com/whythisuniverse.